Hey, everybody. It's Thursday, May 20th. And as you can see here in the aim for today, our goal for today's video is to talk about waves. Now, this is going to be the first in a series of videos on waves. Waves is a pretty long unit. It is more likely than not going to be the last unit we cover for the year. There's a lot of just new facts we have to learn, a lot of important concepts. There are a lot of interesting little phenomena that we cover here in the waves unit. And so this will take us a little while. But as we get started, we really have to ask just a series of basic questions. And that's really what we're going to do here in this video today. We're really going to start off, and this is going to be the broad discussion for today, by asking two questions. And the two questions we're going to start off by asking here, well, one of them is shown on the screen. How can we describe the difference between wave motion and particle motion? And the second question is, what is a wave? And so to answer the question, what is a wave, we really can't answer that question, what is a wave, without first comparing wave motion to particle motion. So really, we're going to answer these two things at the same time. And so the first thing we could say, the most important thing we can say about a wave, what makes a wave different from a particle, is that a wave transmits energy without transmitting matter, whereas a particle transmits both matter and energy. And so the example that I usually give in class when we're discussing this is like a baseball. If I want to transmit the energy that I can put in a baseball, which would be kinetic energy, I cannot transfer that energy from one point to another without the baseball going along with it, right? Like the kinetic energy that a baseball has can put a hole in a wall if you throw it hard enough. But the point is, I cannot get the energy from my body to the wall by using the baseball without the baseball and its kinetic energy going along with it. What makes a wave different from a particle is that a wave transmits energy without matter going from point A to point B. Only the energy goes from point A to point B. And so if we have to answer the question, what is a wave, without talking about particles, the best thing we can say is a wave is energy. A wave is essentially energy while it's moving from one point to another. And when energy moves from one point to another, it moves as a wave. Before we move on, take a second to pause this video here and write that down. When you hit play, we'll move on. Okay, so one of the big things that you're going to see in this, at least first day today, is that because we are talking about waves which are, at the end of the day, fundamentally different from particles, we have to describe them in a fundamentally different way. And this fundamental difference between waves and particles results in us having to use a lot of new vocabulary to be able to describe their differences. So what you're going to see here in the beginning is that we're going to be throwing out a lot of new vocabulary words. And one of these vocabulary words can be seen in this question, because obviously we have to ask ourselves the question, what causes a wave to be sent out through space? Now, we don't use the terminology sent out through space in physics, so we use a new piece of vocabulary, and that word that describes how a wave travels is propagate. So when we say a wave travels through space, we say it propagates through space. But it's important to realize the word propagate just means travel, essentially. And so a wave propagates, saying a wave propagates through space is exactly the same thing as saying a wave travels through space or sent out through space or whatever. So the question says, what causes a wave to be sent out through space or to propagate through space? A wave is a vibratory disturbance that travels through a medium. Now, that's another piece of new vocabulary that would be important to make note of. A medium is a material through which the wave travels. So waves can travel through water, as you've seen before, I'm sure, because we live in a coastal city. They can travel through air, like the sound wave that you are hearing literally right this moment as I am talking. They could travel through a string, a slinky, whatever. And so we can say here that all waves are caused by vibrations or oscillations. And I think getting down the example of just the noises you are hearing right now is pretty stunning. The reason why you are hearing my voice is that deep inside of my throat, my vocal cords are vibrating. The vibrations of my vocal cords, because there is air surrounding my vocal cords, is causing the air around my vocal cords to vibrate. Essentially, what's happening is my vocal cords are smashing into the air, and the air is vibrating. That causes the air in my throat to vibrate, and when it hits the air outside of my mouth, it causes that air to vibrate. The vibration of that air is making a tiny little piece of metal in my computer vibrate. That vibration is converted into an electrical signal. That electrical signal tells the speaker in your computer or phone or headphones or whatever you're listening to vibrate. And the vibration of that little piece of metal in your speaker is smashing into the air and causing the air molecules around you to vibrate. And the vibration of the air molecules around you is causing a little flap in your ear called your eardrum to vibrate, which is converted into an electrical signal that is sent from your ear to your brain. Your brain recognizes that it is sound and that those vibrations that it is hearing are something that you recognize as the English language and words that you are familiar with. And your brain, sort of decodes that in a way that you can understand. It's pretty wild. Waves are caused by vibrations. Take a second to pause this video here and write that down. When you hit play, take a look at a quick demonstration. Here's a quick demonstration. Now, before we move on, I just want to address one point here very quickly. If you look at that last line there, it says all waves are caused by vibrations or oscillations. And so ordinarily I put that up in class and I don't say anything about it. And then somebody raises their hand and says, what does the word oscillate mean? And I say, I'm pretty sure you've seen the word oscillation before. And somebody thinks and sits there and thinks, where have I seen the word oscillation before? And eventually somebody raises their hand and says, I'm pretty sure I've seen the word oscillation on a fan. The way the word oscillation is used for a fan is exactly the same way it's used in physics. It means the same thing. Now, I actually don't have an oscillating fan here, so I would show it to you if I could. I only have like a little box fan. But the word oscillate, when you put your fan in oscillate mode, causes your fan to just turn back and forth between two extremes. That's what an oscillation is. An oscillation is motion back and forth between two extremes. So you can say a vibration is just like a little momentary vibration, or it's a continuous vibration. And when something is vibrating continuously, moving back and forth between two extremes, we call that an oscillation. And so since that is an important piece of vocabulary, it would probably just be a smart idea for us to write that down. An oscillation is motion of an object between two extremes, when it just moves back and forth and back and forth and back and forth between two extremes. Take a second to pause this video here and write that down. When you hit play, we'll move on. So that's it. Big picture concepts covered so far. A wave transmits matter. That's backwards. A wave transmits energy without transmitting matter, and a wave is a vibration caused by vibrations. Sometimes those vibrations are regular and repeated, and so we refer to them as oscillations. Now, before we move on to new definitions and other information, it's probably important for us to just take a brief moment to go over some examples of waves that exist in the real world. These really are only going to be common examples of waves that you'll see in this course. Mechanical waves. Ocean waves are a pretty good example of those. A wave that travels through a slinky is a good example of those. Mechanical waves, like ocean waves, are one type of wave we'll be seeing. Sound waves, although sound waves are technically mechanical waves, generally we refer to them as their own thing because obviously sound, while being similar to, is fundamentally different from like a wave traveling in a slinky. And electromagnetic waves, or light waves. Now, we mentioned electromagnetic waves in the last topic when we were talking about electromagnetic induction, when charged particles accelerate they generate electromagnetic waves. Electromagnetic waves are just light, and we'll be getting to that later. Take a second to pause this video here and write that down. When you hit play, move on. Now, another issue that comes up a lot in Regents physics questions is the difference between a pulse and a periodic wave. So the question then should be asked, how can we describe the difference between a pulse and a periodic wave? A pulse is a single short disturbance that moves from one point to another in a medium. So it would be perfectly acceptable to try to remember this by thinking about like your own pulse. The pulse in your body is just a single boom, boom, a single short disturbance. But the part where that breaks down a little bit is when we look at the definition of a periodic wave, because a periodic wave is a series of regularly repeated disturbances in a medium. And when we say a series of regularly repeated disturbances, that would really be more like your heartbeat, because your heartbeat beats in a series of regular repeating patterns. That's the idea. Take a second to pause this video here and write that down. When you hit play, we'll move on. So now that we've discussed a couple of important features of waves, I would like to demonstrate those concepts to you now. And in class, I like to use this to demonstrate those concepts. Now, this device is obviously not like some fancy scientific apparatus. It's literally just kebab skewers and duct tape. But it gets the job done because, as we said before, a medium is any material through which a wave can travel. And the reason why I like this demonstration is because it covers basically every single thing that we've talked about so far. A wave is caused by vibrations. It results in vibrations, and it travels through a medium, as we see here, and it transmits energy without transmitting matter. Now, if you notice in this video here, this thing is crooked a little bit, and that's really just because ordinarily I get someone else to help me hold this, and I don't have to film it when we're in class, and so I had to use these clamps to be able to make it work. Don't worry about the fact that it's crooked. It doesn't change anything about the situation, really. So what I'm going to do is I'm going to take my hand, and I'm just going to vibrate one of these kebab skewers, and I'm going to move this back here so it tightens a little bit. Okay. And when I take my finger and I vibrate one of the kebab skewers, just watch what happens to the rest of the setup. So as you can see here, when I strike the end and I vibrate this kebab skewer, because all of the kebab skewers are connected to each other by this duct tape setup here, the vibration that happens at this end transmits the energy down to the other end of the kebab skewer duct tape rope-like thing. And that's how a wave works. A vibration at one end causes a vibration in the other end. And if we get it to stop shaking, then you can really see just one little flick will individually travel down the length of the rope. The idea here is that when I cause a vibration over here, that vibration travels without transmitting matter. Now, how do we know it's not transmitting matter? Well, because you don't see any of the kebab skewers actually moving from end to end. 0 kebab skewers travel from one end to the other. The only thing that's traveling is the energy associated with the vibration. And we can tell that because if I make the vibration down here very small, then the rest of the thing vibrates a little. And if I make the vibration down here very large, then the rest of the thing vibrates a lot. And so that's how it works here. Waves transmit energy without transmitting matter. Okay, so while pulses are important because they are a type of vibration and therefore a type of wave, periodic waves are certainly more important as far as physics in general is concerned, and as far as this class is concerned, because periodic waves have a lot of interesting characteristics and exhibit a lot of interesting behaviors. And so while you need to know what a pulse is, and you need to tell the difference between, you need to be able to tell the difference between a pulse and a periodic wave, we are definitely going to spend much more time this year focusing on periodic waves. Now, one important thing you definitely need to know is that there are two types of periodic waves. The first important type of periodic wave is called a transverse wave. And a transverse wave is a wave where the direction of particle vibration in the medium is perpendicular to the direction of wave travel. So you can tell that a transverse wave is a transverse wave if you look at the direction the wave is traveling and you look at the direction the particles are vibrating. If the wave's moving in one direction and the particles are vibrating in a direction which is perpendicular to that, then it's a transverse wave. Now, a good example of a transverse wave, just to familiarize you with the situation you might already be aware of, is a wave in the ocean. Notice if you've ever swam in the ocean, and if you don't, then maybe you've just observed it. I'm sure if you like Google Coney Island beach or something and watch people in the water, you'll see it. If you imagine you're in the ocean and there's a wave coming in from the ocean, notice the wave travels from out in the water to the shore. So the wave is moving in a direction toward the shore. But when the wave comes by, your motion is not toward the shore. If you're 100 feet away from the shore and a wave comes by, you don't go toward the shore. You go up and down. Now, maybe it carries you a little bit towards the shore, but for the most part, your motion is just up and down. That would be a transverse wave. The other kind of wave is called a longitudinal wave, which is a wave where the direction of particle vibration in the medium is parallel to the direction of wave travel. Now, how are you going to remember this? The way that I always remembered it when I first learned this is that a longitudinal wave is a wave where the direction of particle vibration is along the direction of wave travel, longitudinal, along the direction of wave travel. They point in the same direction. Take a second to pause this video here and write that down. When you hit play, we'll move on. So, two types of waves, transverse, longitudinal. I think the main point that we want to make here, that the key distinction is the direction of vibration of the particles in the medium. The waves are always going to be traveling in a certain direction. To be able to tell the difference, you just need to look at the direction in which the particles are vibrating. Take a second to pause this video here and write that down. Hit play. We'll move on. And because this is a little confusing in the abstract, just like reading the definition, let's take a look at an example of both types of waves. Okay, so let's demonstrate some of those concepts. So here I have a slinky set up. This will be the medium through which the wave travels. And to sort of make this a little easier for you, I've put a little white piece of duct tape on here so you can really visually notice the direction of the motion of the particles. And so in every instance, in both instances, I should say, the wave is going to be traveling this way. So the direction of wave motion is going to be in this direction. What you need to pay attention to is the direction in which the particle is vibrating. So here we go. Sorry, I know that sound is excruciating, but notice while the wave is moving this way, the piece of duct tape is moving this way. And if the direction of wave motion is that way, and the direction of the particle vibration is this way, then I hope everybody realizes those are perpendicular. And so that's a transverse wave. Now, I think it's probably also important to realize, and I'll do this again, the thing that determines whether it's a transverse wave or a longitudinal wave is all about the direction of the vibration of the source. So notice the wave can only travel in this direction along the slinky, but my hand is moving in a direction perpendicular to that. And that's what makes the particles in the medium vibrate in that direction. If I do the opposite of that, instead of vibrating my hand like this, I vibrate my hand like that. Watch what happens. If I vibrate my hand back and forth like that along the direction the wave can travel, then what we get is a longitudinal wave because the particle is moving back and forth like this in a direction which is parallel to the direction the wave, the vibration of the particle is parallel to the direction the wave is traveling. Okay, so just to show that in picture form, we have this little diagram here. So the key thing to notice in both of these diagrams is that the wave, in either case, is traveling from left to right. And I'll mark that with a V just to say that's the direction of the wave velocity. And so to generate the transverse wave, the particles are vibrated in a direction which is perpendicular to the wave's velocity. And so we get a transverse wave. And to vibrate the particles in a direction parallel to the wave velocity, the source down here vibrates parallel to the wave's velocity, and so we get a longitudinal wave. Now, something they're going to ask about, and I understand that this video has been information heavy, but that's just kind of how it goes here in the very beginning, is that A, the key distinction is the direction of the vibration of the particles in the medium. Now, we already said that, but that's like the important part. So that's something you're going to want to pay attention to. And something else they're going to ask you about are examples of periodic and longitudinal waves, because two of the types of waves that we've already mentioned today are either transverse or periodic. So here's what they're going to want you to know. They're going to want you to know, and you will see this in questions when we start to do them for homework, that light is a transverse wave. Furthermore, what they want you to know about light, and the only reason I'm mentioning this here is because the question always asks about both of these things at the same time. What you also need to know about light is light does not need a medium to propagate. Light is a unique wave in that sense. The easiest way to think about it is to think about space. Space, outer space, is a vacuum, meaning there are basically zero particles out there. There's no oxygen, there's no atmosphere, there are no particles. And yet, the sun, which is 93 million miles away, generates light, which can travel through the vacuum of space. So light does not need a medium to propagate. On the other hand, an important example of a longitudinal wave is sound. But sound does need a medium to propagate. There is no sound in space because there is no air in space. Sound, as I mentioned before in the very beginning of this video, is just the vibration of air molecules. And I think the point is, if there are no air molecules to vibrate, then there is no sound. Now, if you've been to the New York Hall of Science recently, you might have seen a demonstration of this. It's pretty cool, and I'm sure you can find it if you Google it. At the New York Hall of Science, they have a chamber. It's like basically just a big bucket-looking thing tilted upside down. And underneath that bucket, or inside of that bucket, if you will, there is a bell. And if you push the button, the bell rings. And you can hear the bell ringing because there's air inside the chamber. The chamber vibrates, and then it causes the air outside the chamber to vibrate, and you hear it. But when you push the button to make the bell ring, there's also another button on there which causes air to be sucked out of the chamber. There's like a big vacuum system, air pump system hooked up to the chamber. And what you notice when you push that button is that as the air is pumped out of the chamber, you hear the sound less and less and less and less until all of the air is pumped out of the chamber. and you hear no sound at all. So if you think about space, that there is no sound in space, but there is light in space, then you can remember that distinction. Light is a transverse wave, sound is a longitudinal wave, and really that's just because they are. That's how they work. But that's something you do need to know to answer Regents questions, and so it's just something you're going to have to remember. Take a second to pause this video here and write that down. Hit play, we'll move on. All right, now that's really it as far as new information is concerned today. But I just wanted to make sure we had the opportunity to just give a formal definition for this word, even though I've mentioned its definition already, because you will see this a lot in questions. The word propagation is just another word for travel or spread. And so wave propagation refers to waves traveling or spreading through space. So when you see the word propagate, that is what it's referring to. Now, before we go for today, I just want to give you a sense of the kinds of questions you'll be seeing on Regents problem sets. And so what I want to do is basically just take a look at 3 of the major questions that they ask on the Regents, which refer to the material we've discussed today. So here's the first one. This is in the Intro to Waves packet on page 2, number 16. It says, a student strikes the top rope of a volleyball net, sending a single vibratory disturbance along the length of the net, as shown in the diagram below. The disturbance is best described as a pulse, a periodic wave, a longitudinal wave, or an electromagnetic wave. Take a moment to look over this question, pause the video, and when you hit play, we'll go over the answer. So you got to pay attention to the key pieces of information they're giving you in this question. And the key piece of information is this one. The student strikes the net, and it sends a single vibratory disturbance. A single vibratory disturbance is the definition of a pulse. And so when the student strikes the volleyball net, this disturbance is best described as a pulse. Choice 1. Now, what I usually ask in class, so I guess I'll just ask this question here too, is let's pretend instead of the student just striking the volleyball net once, if they struck the volleyball net the way it's being shown here, if they struck the volleyball net over and over and over and over again, and the disturbance was sent out along the net in this direction, we would get a periodic wave, because it would, instead of being a single vibratory disturbance, would be a set of regularly repeated disturbances. But the question is, which type of periodic wave would it be? If the strike went down like this, and the disturbance went like this. If the person struck the volleyball net like this, all of these particles in the volleyball net would vibrate up and down too. And if the particles in the medium, which is the volleyball net here, are vibrating up and down, but the wave is propagating from left to right, then that would be a transverse wave. Here, it's not though, of course, because when the student strikes the volleyball net, in this instance, it's a single vibratory disturbance. All right, let's take a look at another one. This one is in the Intro to Waves packet, page 2, number 17. It says, which diagram below does not represent a periodic wave? Take a second to look at the choices. Think about what the answer is, and think about why the answer is what it is. And when you hit play, we'll go over it. Okay, so the only thing you really need to know to answer this question is what the definition of a periodic wave is. A periodic wave is a series of regularly repeated patterns. Looking at the answer choices, choices 1, 2, and 3 are regularly repeated patterns. The first type of wave is called a sine wave because it looks like a sine function. The second type of wave is usually referred to as a square wave, although it's not quite square in this diagram. The third type of wave is called a sawtooth wave because it looks like the teeth on a saw. The fourth wave is not periodic. And the reason why it's not periodic, and we have a word for that, it's called aperiodic. The reason why the fourth diagram is showing you an aperiodic wave is because the disturbance or the disturbances are not regularly repeated. This one in the beginning is short, this one at the end is long, this one in the middle is medium. And so because these are not a regularly repeated pattern, which I think is obvious enough when you look at all four diagrams, that wave is not periodic. Okay, and last one for today. This one is in the Intro to Waves packet, page 2, number 11. It says, a pulse traveled the length of a stretched spring. The pulse transferred, and you have four options. Take a second to look this one over. When you hit play, we'll go over it. Okay. The fact that this problem says it's a pulse that's traveling the length of this stretched spring is totally irrelevant because pulses and periodic waves are both waves. And the essential characteristic of a wave is that it transfers energy without transferring mass. If you looked at the slinky, or if you looked at the kebab skewer and duct tape setup, while the energy was traveling down the length of those media, keep in mind here, media is the plural of medium. While the wave traveled down those media, the actual particles of the medium, whether it was the kebab skewers and duct tape or the metal pieces of the slinky, those were not traveling. Only the energy from the shaking or the vibrations were traveling, and those particles were just moving back and forth. The essential characteristic of a wave is that it transmits energy without transmitting matter. All right, guys, that's it for today. Tomorrow we will dig a little bit deeper into periodic waves and start to discuss some of their characteristics, and then move on into some more complex wave behaviors.